Hello, how are you? All right, so this is section number 8. And section number 8, I'll break this video into two. So the first part of this video will start from pages 89 to pages 96 of your test. Okay, I said it again. So this will cover pages 89 to pages 96 of your test. Is that okay? And I would want to start. Okay. Now, so far, really, this unit 2 starts from section 7 to 12, and there will be a lot of formulas that will be generated. Okay, during this period, actually the remaining of the sections. So there's a yellow sheet right at the center of your book, and that is on pages 235 and 236. There's a formula sheet provided. Okay, so you can always use that formula sheet. But as and when I refer to this formula sheet, I'll let you know. Okay, so that's just by way of information. All right, now here we discuss scatter plots and linear models. Now, this is a very important concept, and it has wide application in finance, in engineering. I mean, across all fields, this is really very important. And it is also important that you understand how linear models work, so this is an important concept. So here, the objective of this is that we will determine and explain the scope of a model, identify independent and dependent variables, find slope and intercept of a linear model, construct linear models giving a starting value and unit rate of change, okay, and the remainder of the objectives that you see on the screen. All right, so let's get into this. So you may have, or you have seen a graph before at this point. All right, so we know that when I draw something like that, okay, we call this the x-axis and we call that the y-axis. Now, we are going to give them some other names, a different name, and the y-axis, another name that you may not know, if you know already, is we call him the y-axis the dependent axis, and the x-axis is the independent axis. Okay, nice. Now there are reasons assigned to why they have these names, dependent and independent. Is that okay? Now when I have, let me explain that for a brief moment. If I have y is equal to 2x plus 3, okay? Now if I choose, say, let my y, so if I have my x to be x value, so let me say this is y is equal to 2x plus 3. So when x is 0, y will be equal to 2 times 0 plus 3, and this is 3. So the coordinates here are what? 0 and 3. Okay, so if I have x to be 1, y will be 2 by 1 plus 3. Okay, so this is 5. Okay, now my x is 1 and my y is 5. Now I can decide to choose all numbers, any number for x, and look at the corresponding value of y. Okay, and these pair of coordinates, so this is x and y, and those can be put on a graph and we can draw the slope. Okay, now you realize that as we change the value of our x, all right, the values of x also changes. Is that okay? Now the reason why we call x independent and y dependent is that the value of y is determined by the value of our x. Is that okay? So x is independent. It assumes its own values, but the value of y depends on the values of x. So we are saying that x-axis is the independent axis, and the y-axis is a dependent axis. Okay, nice. Now, so here, so the graph we just looked at, like the values I will just put in, I will just generate. And if you decide to put these on a graph, this is how they will look like. Okay, sometimes you have a straight line and sometimes you do not. All right, so when you put the points, the coordinates on the graph, this is what we call a scatter plot. So below is a scatter plot of data representing the consumer price index. Each dot represents the CPI for a month from January 2011 to April 2016. And there are 64 months of data. So there are 64 data points. Is that okay? Nice. Now, the independent variable are the values found along the x-axis, the horizontal axis of the graph. And what is the independent? The independent is the months after January 2011. Okay. Now, why might it be called independent? Time operates independently of all other things. So time is independent. Everything we do depends on time. Okay. So time is an independent variable. Note that. So all the time, anytime you use time, we will see that time is independent. And we will reference that a lot once more. Now, dependent variable are all the variables found along the vertical axis. And what's the vertical axis? That's the consumer price index. So when I look at the time, I can look at the corresponding CPI, right? So for every year, I will be able to find the corresponding CPI against it. Now, data is graphed by ordered pairs. And by ordered pairs, these are coordinates like I generated at the early part of this video, okay? And those are x and y. So if I know my x value, I can find my corresponding y value. Is that okay? Nice. Now, a positive trend occurs when as one variable increases, the other variable also increases. Now, what do you see here? On this graph we have up here, this assumes a positive trend, okay? So you realize that as x values increase, the y values also increase. Is that okay? So I'm going to show you two different graphs that depict a positive trend and a negative trend. Now, if on the other hand, if I have a graph, so this is for a positive slope, and this is for what? A negative slope. So in A, you realize that as the values of our x increase, the values of our y also increase. Now, on the other hand, as the values of our s increase, okay, we realize that the values of our y is what? Is decreasing. And this is a negative trend. And that is what? A positive trend. Okay, nice. A positive slope and a negative slope. Okay, we will really go through that in more detail soon. Now we talk about linear correlation coefficient. Now, statistical studies relating to two variables often report the strength of a linear correlation or relationship between variables. Correlation is a relationship between variables. Is that okay? Now, the positive correlation is when data follows a positive trend, and a negative correlation is where data follows a negative trend. And we shall see that. So here, now assessing linear correlation. So we want to assess the linear correlation. Now, this is data we have. So for instance, so for that, so this is a scatter plot. So when you put the pair of coordinates on the graph, this gives you what? A scatter plot. Okay, so we have these, and we're going to use this to determine the behavior of the trend. Now, when we draw a straight line through these points, and that's what you see below here, you realize that the line is able to go through a lot of the points, okay? And you realize that this is a positive trend because as one variable increases, the other also what? increases. So we say this is a strong positive correlation because this line goes through majority of the points. Now, for the second one, if I draw a straight line through this, you realize that though this is a positive trend, very few of the points fall on the line, okay? So we're saying that there's a moderate positive correlation. Now here, if I draw a line, it's possible, you realize that no linear correlation. This is scattered all over the graph. Is that okay? So we say that there is no linear correlation, okay? And then right there, if I draw a line, okay, it goes through few points, but this is trending downwards. So we say this is a moderate negative correlation. And you go there, and the line goes through many points. So we say this is a strong but negative correlation because this is trending downwards. Is that okay? Nice. So this is just the behavior or how to measure correlation. Is that okay? Nice. Now, correlation versus causation. Correlation is a mathematical relationship and does not imply causation, right? So two variables may be related, but does not mean that changes in one variable affect the other. So now let's look at this table right there. So correlation and relationship, time spent studying and test scores. We expect that if you put in more time, okay, studying for your test, you should get what? A good score. And number of appliances in the home and the cost of electricity bill. So we expect if you have more appliances at home, you should expect to pay more on electricity, right? So there is a correlation between how many appliances in your home and the bills you pay. Is that okay? Now, let's look at causation and effect. Taking a test and earning points. So the fact that you take a test does not mean that you earn the points if you don't do the right thing, right? Not paying bill and no electricity, okay? And then smoking and lung cancer, fluctuating cost of a barrel of oil and cost of gasoline. So this is the distinction. So correlation does not necessarily imply causation. Okay, nice. Now, so we spoke about the trend line, okay, and the trend line for this data set that we have for the CPI, this is what we call the trend line equation. Okay, and usually you'll find this on the graph. And that is what we call the trend line equation. Okay, now we want to find 224.85 on the y-axis. Okay, what happens at that point? 224.85. That is right there, right? That's the starting point. That's where the trend line begins. So usually, the name we give to this guy is, we call it the y-intercept. Y-intercept. And the y-intercept is where the trend line cuts this y-axis. Okay, and we are going to know that this is what we call the slope of the equation. And we will label that soon. Now, where does that value appear in the trend line? At the end after the sign, right? So that is right there at the end. Now, the linear model begins with 0.246. This means CPI is increasing. So this is the interpretation of the slope guy. So this value, when this value is positive, we say there is an increasing trend. And when the value here attached to the x is negative, we say there's a decreasing trend. Okay, so the linear model begins at that. This means that CPI is increasing 0.246 for each month after January 2011. Now, what CPI value does the model predict for January 2011. And for January 2011, because this is the starting time, okay, we plug in 0 for our X, and the CPI predicted for January 2011 is 224.85. Now, how would you use this linear model to estimate the value for February 2011? So for the same year, you have to plug in, because the starting month is January, right? So February is going to be month 1. Is that okay? So you plug in 1 for your X on this same equation, and that gives you 225.10. Okay, nice. Now use the equation to estimate the CPI for January 2016. Okay, so for January 2016, you look at how many months are there. So the starting year was January 2011. So between 2011 and 2016, how many years are there? We have 5 years. Now, how many months are there in every year? We have 12 months in every year, and that gives you 60. So you plug in 60 for your X, and that gives you the predicted value. Now locate the dot that represents the the actual CPI value for January 2016. So you look at this side and you look at that. Now you want to compare that to the predicted. So the actual, you realize that the actual is what you find on the graph, and this number is the predicted. So if you want to compare the two, you realize that the actual is less than the trend line value. Is that okay? So the actual value is what you see on the graph, and this is the predicted or the estimated value. Now, should the linear model give the actual value? Explain why or why not. So the linear model gives the estimate. It is typically not the same as the actual. The actual is what you see on the graph. Is that okay? Nice. Now, we want to talk about what we call the scope of the model. Now, the scope of the model refers to the range of values of the independent variable, and it is not recommended that the model be used for estimating values very far outside the scope of the model. Now, since the trend line may change outside the range of values for which there is a data, right? Now, when we talk about the scope of the model, is where the first dot starts on your graph and where the last dot ends on the graph. You trace that to the x-axis, and the range of values that are there, this point and that point, these values, the values here and there, are what we call the scope of the model. So here, the scope of this model is 0 to 63. Is that okay? So where the first that starts, okay, you trace that to the x-axis, versus where the last that ends, you trace that to the x-axis. And the range of values, here we have 0 to 63, and that gives us the scope of the model. Now, would it make sense to estimate the CPI in the year 2030 from this data set? No, because we've been advised that it is not recommended that the model be used to estimate values far outside of the scope. So 2030 will be outside the scope. So it is not advisable for us to use the model to predict values that are outside the scope of the model. Okay, nice. Now, so now let's begin taking some practical examples. So here we have life expectancy at birth versus GDP per capita, right? And we want to consider the graph to the right. And would you say that there's a strong, moderate, or weak correlation between life expectancy and GDP per capita? Now, when you look at it, this trend line only goes through very few points. And though it is trending positive, there are a lot of points outside, okay, outside of the trend line. So we say this is a weak positive correlation. because there are many points outside of the trend line. Okay. Now, what is the scope of this model? And we agreed a while ago that the scope of the model is where the first dot starts. So you trace that towards your x-axis versus where the last dot ends. You trace that to the x-axis, and the range of values here is what we call the what? The scope of the model. So what would the scope of this model be? The scope is from $0 to 145,000. And that's the scope of our model. Is that okay? So be careful, don't trace it towards where the line ends, but look for the last dot versus the first dot. Okay. Nice. So that is the scope of the model. Now, should we use the model to predict life expectancy beyond 150,000? Nope, because that is beyond the scope of the model, because the scope of the model was between what? 0 to 145,000. So it's not advisable to do that. Now, what is the linear model or the equation for the line? And that has been given to you as this guy. The linear model or the equation of the line has been given to you as y is equal to 0.002x plus 66.819. So this is the linear model, okay, or otherwise the trend line equation, or you can call it the trend line equation. Okay. Now use the linear model to estimate life expectancy when x is 102,000. So you plug in 102,000 for your x, and the life expectancy is 87, around 87 years. Okay. Now, how does this compare to the actual? So here you are looking at 102,000, right? So 102,000. So we are looking at Luxembourg. So Luxembourg is right there. Now, what you estimated versus the predicted, how will you compare that? The model overestimates the actual. So you realize that this is higher than the actual value here if you trace that to the y-axis. Is that okay? So the model overestimates that. Okay, nice. Now here we start our conversation about the slope of a linear model. Okay, slope of a linear model. So we have established, or we know that a linear model is y is equal to mx plus b. Now this guy is what we call the y-intercept. And the y-intercept is where the trend line cuts the y-axis. And this guy is what we call the slope right there. Now, if this number is positive, we say that there's an increasing trend. And if this number is negative, we say there's what? A decreasing trend. Is that okay? So we are going to go into details as to how we can find, we can look at the slope. Now, the two graphs we have here, we have purchasing gallons of 2% milk, total price, and then the number of gallons purchased, and purchasing gallons of organic milk, the total price versus number of gallons purchased. Now, where does each graph begin? And you realize that each graph begins at 0, 0, right? So if you buy 0 milk, we expect you to pay $0, okay? Now the two graphs have the same scale on both the x-axis and the y-axis, but one looks to be steeper than the other. Why? Now one is steeper because organic milk is more expensive. Now this means that I'll start from my left right there. Now if I buy a gallon of 2% milk, how much do I pay? I just pay $3. and 30 cents. If I buy a gallon of organic milk, and this is how much I pay, I have to pay $6.49. So because this is cheaper, is that okay? We say organic milk is more expensive. So the number of gallons versus how much you pay. So if you buy 2 gallons, this is how much you pay. But if you buy 2 gallons of 2% milk, you pay 6.60. Okay, nice. How much is a gallon of that, and how much is a gallon of organic milk? Okay, so you should tell that. So this is 1 gallon of 2% milk and 1 gallon of organic milk. Okay, nice. Now we will learn to look at how we can find the slope, okay? And the slope, which I already showed you, M is equal to the rise over the run. And usually we say the slope is changing y, which is y2 minus y1 over x2 minus x1. Okay, now if we pick any pair of coordinates on both ends of this slope, so for instance here, if I want to pick the pair of coordinates here, this would be x is 1 and this is 3.30. Okay, and here we have when x is 1, we have the cost of organic milk being 6.49. Okay, now if I pick any 2 pair of coordinates, I should be able to get the same value for my slope. And let me say we pick 3. So for 3 gallons, is that okay? We want to know that the cost is that. Okay, and then let me say if we pick 4 right there, so 4 gallons, and how much is that? 19.4. Okay, now this is how you identify them, and we are going to put them right here in this formula. So this is the value, the first coordinate is x1, this is what? y1, and this is x2, and that is y2. Now you put these values in our graph, in our formula, right? So if I want to find the slope, so y2, I have y2 to be 9.90. So I'm taking the first graph minus y1, which is 330. If I take x2, x2 is 3 minus 1. Okay. If I do that, I should be able to find the slope. Now, so 9.9, so 9.90 minus 3.3. That should give me what? 6.6. And this is what? 2. 6.6 divided by 2 gives me what? 3.3. So my M is now equal to 3.3 right there. And we are going to realize that now we did the slope for the organic milk. This means that for every gallon of organic milk, I pay 6.49. And then the slope I just found for 2% milk means that for every gallon of what? 2% milk, I pay $3.3. Okay, nice. So that is what the slope really means. The interpretation is as simple as it relates to the graph. Okay, nice. Now here, y-intercept, and we have already established that the y-intercept is where the trend line cuts the y-axis. So where does that begin? It begins at 54. And other groceries in the cart cost this much. Okay, nice. Now, what is the y-intercept or B of the model? So here the y-intercept is still there where the trend line cuts the y-axis. And what was the y-intercept or B when we only purchasing milk on the previous page? That was what? 0. All right. Now we want to put these pieces together, and we want to form what we call the equation, the trend line equation. Now we consider the graph at the top of the page. We found our M to be what, 3.3, and we found our y-intercept to be 54. Okay. Now we want to substitute these into the formula, and we have that and that. So our trend line equation, y is equal to 3.30 x plus 54. Okay. Now we can use this to model, and that's what we call the linear modeling. We can use this to model real life scenarios or situations. Now, David weighs 240 pounds and sets a weight loss goal of 2 pounds per week. Is that okay? Now, let X represent the number of weeks which go by. Find a linear model which represents how much David hopes to weigh after X weeks of the plan. What will the dependent variable be? Okay, now we have established that time is always independent. So time is always our X, right? And any other thing else. So now, what unit? So our Y will be the pounds, and our X is going to be the time on diet in weeks. Now, what is the y-intercept? The y-intercept is the starting point. So David's weight was at 240 pounds. So that is our y-intercept. Now, what is the slope? The rate of change. The slope is the rate of change. Now, he sets a weight loss goal of what? 2 pounds per week. So this value is going to be negative because that is the rate of change. He sets a weight loss goal of 2 pounds per week. He wants to decrease by what? 2 pounds per week. Now we want to put these pieces together on our equation y is equal to mx plus b. And we just assemble these numbers and get our linear model. Is that okay? So we can use this to estimate how David is going to weigh, okay, given the weeks. Is that okay? So if you want to know David's weight in 4 weeks, we just plug in 4 for our X, and that will be David's weight. In 10 weeks, we can use that to also estimate what David's weight will be. Okay. Now, how long will it take David to weigh 180 pounds? So we can as well find that. So already we have our Y is equal to minus 2X plus what? 240. Now we want to know our X from this point. From this problem, we are given the pounds. So we want to know the time. Okay. So we solve this linearly. So this is going to be 180 minus 240 is equal to minus 2x. Okay. So 180 minus 240 gives you 60 negative, and you have that. So you divide by 2, you divide that by negative 2, and your x is what? Just 30. So it will take David 30 weeks, okay, to weigh 180 pounds. Isn't this beautiful? Okay, so really this is linear. So David's weight loss equation. Now you could see that this is a negative trend because his weight is trending downwards. Okay, so as the weeks increase, okay, we expect his weight to drop. Okay, so that's the model. Now, if David decides to extend his weight loss goes to 3 pounds per week, the graph gets steeper downwards, right, in the negative direction. And this is what the graph will look like. Now, David could not do this weight loss indefinitely, right? It would not be advisable for David to do that indefinitely. All right. So here, this is the Excel application, how you can use Excel for linear modeling, and the steps have been outlined in your book, so you can give it a shot. And that's I would like us to end here for the first part of this section. And so far, we have been looking at the scope of the model, right? But even before we look at what a scope is, we said X is referred to as the independent axis. Okay. And our Y is called dependent, the dependent axis. Is that okay? Now, we said that they have these names because the value of X determines the value of our Y. So therefore, X is independent and Y is what? Dependent. And then we also looked at the scope, and we said for the scope is where the first dot starts and where the last dot ends. You trace that to the x-axis, and the range of values would always give you the scope of your model. And it's always not advisable to use the equation to estimate values outside the scope of the model. Is that okay? And finally, we looked at y is equal to mx plus b. And basically, this will be the center of our discussion. And we know that b is called our y-intercept. And the y-intercept is where the trend line casts the y-axis. And we call this guy the slope. And the slope is found by the rise over the run. So change in y over a change in x. Okay, and that is how. So basically, the focus is going to be on y is equal to mx plus b, and that is basically linear modeling. Is that okay? So let's take a break here and watch out for the remaining part of this section in another video. All right, so thank you and see you soon. Bye.